time, but let's write down the Maxwell's equation. This is the full Maxwell's equation are these ones. So we'll start talking about magnetics. I mean, once you have currents, then you can start talking about magnetics. Okay, good. And now, so what we've been doing is working at lowest order in 1 over c, right? And at lowest order, 0th order, let's leave off the media for now. Okay, so at 0th order, we were solving these equations. Okay, rho, and then curl of B, 0, 0, and divergence of B, 0, 0, and minus curl is equal to 0. Okay, at lowest order, right? And now we're solving systematically. So we're solving in powers of 1 over c, right? Which is essentially all that you ever do as an undergraduate. Okay, and now at 0th order, right, you can set b equals 0. That's easy enough. Okay, and now we should proceed on to 1st order. Okay. So at 1st order in 1 over c, we get some equations, right? So now I look at this at 1st order in 1 over c. I remind myself that b of 0 is 0, right? So this term in particular starts like 1 over c squared. And it's the familiar that the changing magnetic flux produces a voltage, okay? So that starts as 1 over c squared because b starts at order 1, and it has a 1 over c in front of it. That's 1 over c squared, okay? Good, so we certainly can neglect that, yeah? And now you're left with, at 1st order, you get sort of divergence of B1 is equal to 0, and now you get curl of B1, right? Is J over C, yeah? And now you get 1 over C, or C is B0. Good, and divergence of B equals 0, and this curl of B.
Can you repeat why it starts like 1 over c squared?
Yeah, so B starts like order B, 0 is 0. So this starts like B1, and there's a 1 over c sitting there, so you get 2 powers of c. That's 1 over c squared. Okay? So, good. And so now we're going to go solve this. So your picture is like that. What do I get there? So what you're supposed to do, let me erase the... Look at these. So first of all, you could set E1 equals 0. Okay. Okay, so let me just eliminate those equations. And so now I'm dealing with these two, which are the equations of magnetostatics. Okay. So what do you get here? So we could write it right, and its curl B1 is some current, which I'll write as J total, okay, and some divergence of B1 equals 0, okay. So J, the total current, we sort of consist of 2 parts. One is the current, physical current, and one is the so-called displacement current. Which is another name for the time derivative of the electric field. Okay? So, and if you think about it, the currents are specified, right? And the charges are specified. So this is a known function, right? Known from 0. So first you're supposed to find the charges as a function of time. Okay? And then at each time, you're supposed to solve these equations, right? And find E0. And then you know the electric field as a function of time, right? And then this serves as like a current. Okay, so now you've specified basically a kind of current that you're going to go solve for. Okay. All right, so we'll do a problem later like that, and not this. Okay. So if I just look at it, so everything I'm going to say today, right? By J, I mean J tote, okay? So I'm going to stop putting the tote, but I mean tote, okay? So J, right, I'm just going to write. So very often you'll just have some currents and you won't have any charges around, and so there'll be no electric field, okay? And in which case this is just the ordinary equations of magnetostatics, okay? But everywhere you write I, you could write I tote, and everywhere you write J, you could write J tote, and everything goes through without a problem, okay? And the Biot-Savart law, all that stuff goes perfectly well through, okay? So I will stop writing the tote, okay? But it's always there, okay? Good, so now let's go on, right? So we're going to go solve this equation. So first of all, of course, Laplace law. Okay. And then what do we get here? So Ampere's law. So we get here. We draw a loop. Any loop. There's some currents. Okay, draw a loop to it. Okay. And the current. And you draw any surface. Okay. Doesn't matter which one. Okay. As long as it's bounded by the loop, and you get the integral of E. Call it dl. Yeah. Equal to integral of curl of B loop over the surface. Okay, and so the curl of B is J, and the integral of J passing through the surface is equal to the current. Okay, so we get here J over C. So there's an extra, try to remember that there's an extra factor of 1 over C from what you learned as a kid, like not I, but I over C. Okay, good. So, of course, simple case, higher currents make magnetic fields. There's current here. Okay, here's this integral. You get B times 2 pi rho from the integral around this loop is equal to I over C. You could be phi if you like. Okay, we'll row is okay. All right, good. So let's just talk quickly about the Biot-Savart law. Okay, so currents make magnetic fields, and that's sort of quantified by the Biot-Savart law, which we should probably somehow derive. From the Maxwell's equations. Okay, so Biot-Savart. Okay, well, what does it say? It says, right. B, I say dB, right? Vector is a sum of J dB times over C, right? R hat, over 4 pi r squared. Okay. Picture would be somehow like this. Let me draw my picture here. Here's J dV. Okay. That's a position, and this is R minus R naught. Good. So if you have just a wire, right, you have to think that through. Okay, so JdV is normally written like I over C. You have just a wire, IDL. Kind of think that through, right? So just imagine that you have a wire and has a little area, okay, and you integrate over the area and over the length. You kind of convince yourself that if I integrate JdV over this volume, that's the same as IDL. I'm drawing that little picture. Okay, good. Okay, so maybe just first, hopefully, familiar. So we're gonna, somehow we're sort of pulling that formula out of the hat, right? We should sort of derive it. Maxwell's equations, right? We should sort of derive it, right? So normal statement, dV is IDL. Okay. So maybe just one very quick example. I mean, I'm not going to do it, of course, but here we go. So if I take a ring current, ring has radius A, right? Traditional undergraduate problem, right, is to find the magnetic field on the ring. Okay, on the line of chart, on the line, so presumably somehow it was done before, right? So if I take here this thing, I get R minus R naught. What do I get? IDL. Get dB is pointing this way. And you would typically break it up if you're only interested in the magnetic field in this direction. Okay. So there's some problem like that, okay? Now, so I'm not going to go through those steps. I'm just going to kind of quote the answer, right? Okay, well, this is sort of super simple, but okay. Anyway, I'm going to quote the answer, which I hope is somehow enough is known. So hopefully sort of familiar expression, so somehow involves e squared plus a squared to the 3/2. And my point for recalling this is not because I don't think you know that problem, right? My point is the following. So let's just remember that at large distances, then you would expect, like, the whole thing would be dominated by the magnetic dipole moment, right? So at large distances, expect this dipole moment. And so, well, the magnetic dipole moment of a loop, kind of just, we'll derive it, but let's just remember it. Okay, so it's what? It's I over C times the area. So for a plane loop, okay, area A, okay, then the magnetic dipole moment here is pointing upwards. And it has units I over C times pi A squared. Okay, and it's in the z hat direction. Good. And so at large distances, you get this typical dipole form. So expand for z large. Then I get typical form. So b in the x direction, z is equal to 2 n 4 pi z cubed. Okay, so there's a factor 2 there. That maybe seems surprising, I don't know. So it's 2 over 4 pi z cubed, but it shouldn't be surprising because it turns out that the formula for the magnetic field from a magnetic dipole is the same as the electric field from electric dipole. Okay? And it turns out that B from a dipole is 3n dot m minus n r cubed. So dipole, unit vector in the radial direction. Okay, so at any point in the plane, you expect this this form. Okay, and you see that if n is exactly on axis, right, and this becomes 3 minus 1, right, which is 2. So that kind of is typical sort of expression you get. Okay, so let's just now sort of derive some of these things. Okay, the dipole formula, B sub r, right? Think about them a little bit further. So let's now go back here. So we have curl of B is J over C. Okay, and divergence of B is equal to 0. Okay, and so now you would, in analyzing these equations, what you would do is say, okay, divergence of B is 0. So I can automatically solve the second equation by writing it as the curl, B is the curl of something. Solve. That's simple, okay? Already solved 2 automatically. And so now we can go ahead and solve equation 1. Take the curl of A and plug it in there. So you get curl of A. Okay, like that. Now you sort of remember this, like I said, back to ABCs. Remember the ABCs? Whenever you see curl cross curl of them, you say, okay, BAC, ABC. And so it turns out to be, back, back. BAC minus A. So nabla nabla is like Gaussian squared, something like that. Gaussian squared. Okay, now you're sort of have to think for a while before you know how to proceed, right? So we use BAC ABC, we get to this form. Now we have an equation for A, which looks not all that simple, right? But there's a freedom, okay? So you can now use your freedom. So A is not unique, right? So A you can always add. You can always add a gradient of a scalar function. Okay, so A can always replace with A plus gradient of lambda. Okay. And since the curl is curl of a gradient lambda is 0, okay, you get the same B field. Okay, so you're free to replace A with another function, new A, okay, just with that replacement. Okay, so you can use this freedom, right, okay, to choose one condition, one scalar condition, right? So you can use this freedom to eliminate this term. Which is now the Coulomb gauge. Okay, so now I've eliminated it. I can eliminate this term, right, by choosing the Coulomb gauge. Right? I don't have to choose the Coulomb gauge, but it's a convenient one here because this term is ugly and this term is not so ugly, right? So now we're solving now the Laplace equation. Vector Laplace equation. So at least if I work in Cartesian coordinates, okay, then this is like 3 Laplace equations in a row. Right? 3 AX. Okay. In free space, right? So we sort of have a lot of experience solving equations like that. So in free space, at least, we know what to do, okay? So in free space, what do we find? It's just the Coulomb law, right? So the current Jx is acting like a charge for Ax, okay? And so you can just integrate d3x. Okay, and now I get here J of x Coulomb law. Okay, good. All right, right, so now you set a formula have at least, solved for the vector potential as written as integral. So j of x is a known function, so in principle, very much like the Coulomb law, you've sort of solved, right? Sort of solved for on A. Okay, so once you know A, you can determine B, right? And since it's the Coulomb law, right, I should get the Biot-Savart law, right? I mean, if the potential is like A, right, and if I calculate the field, I should get 1 over r squared and get the kind of Biot-Savart law. Let's see how that works out. Okay. There's a trick to it.
So is there a reason why this formula for A necessarily has to satisfy del dot A equals 0? Is that it just should, right? Is there an easy way to see that?
Yeah. Yeah, because at the lowest, it's a 1 over c missing. So divergence of J is equal to 0, right? And so at the order we're working at, so I think you can go ahead and take the divergence, integrate 1 spec parts, so you'll take the divergence, integrate 1 spec parts, and get that thing instead. Okay.